Hi, in this video, we will learn how to perform the Laplace transform by using the property 3, which is the derivative and also the integral of Laplace transform. We know that when we perform Laplace transform for the ft, you will get fx. How if you multiply the t and then you perform the Laplace transform for this thing? You will find that when you multiply t here, in the Laplace domain, you will need to differentiate it with respect to x, and then you have to take the negative. If you divide the ft function with respect to t and you take the Laplace transform for this, you will get the result in integration. So you need to integrate the fx from the limit x to infinity. So normally we will replace the x to be x bar here to indicate the dummy variables. In property 3, you see that when we multiply the time domain signal by t or divide by t, we will deal with the differentiation and integration in the Laplace domain. So instead of call it as the derivative of the Laplace transform, we also can call it as the multiplication by t property. So for the integral of transform, okay, we can also call it as division by t property. This is the proof for the property 3. This is the definition for the Laplace transform, where you take the Laplace transform of the ft, you get this integration. So if your function is t multiplied with ft, then you substitute the function to be tft here. If you have the function to be t square ft, then this will be the new function. And if you have a new function like this, then you substitute it here also. Let's assume we don't know this answer in the first place. So to find the answer for this, we try to differentiate the fx. Okay, so if you differentiate the fx with respect to x, so we can substitute the fx to be this inside here. So this is our fx. Now we differentiate it with respect to x. Then we take the differentiation first with respect to x for the component inside, and then we can get into this because the ft is a constant for with respect to dx, and when you take the d over dx e negative xt, so in this case you obtain the exponential negative xt remain, and the constant negative t can be multiplied in front here. When you compare this function and this function, you found that this is in negative, this is positive. So to get positive, so we have to multiply with negative 1 here, right? So on both sides, so you should, on your left hand side, you should get negative d over dx fx. So you found that negative d over dx fx will be equal to this. Let's continue to differentiate this term with respect to x. So let's say if you differentiate it, you get d squared over dx squared. Here also. So over here you have d squared over dx squared. Then for the exponential negative xt, okay, so if you differentiate once, you get negative t. You differentiate again, you get negative t again. So this to be in power of 2. So negative t squared is equal to t squared. Right? And then when you compare this term and this term, you found that over here there is additional negative term here. So therefore you have to minus it again on your left hand side. So it becomes positive. So this one is positive. So we can say positive d squared over dx squared for your fx is equal to this term. If you continue for the Laplace transform for t power of 3 ft, then you should expect your answer to be negative. So negative, positive, next one is negative d power of 3 dx power of 3 fx. So we can see the pattern when you multiply with t power of 1. So over here it will be negative 1 power of 1, right? You still get negative 1. And if your t equal to power of 2, so over here is negative 1 power of 2, which gives you the positive. If you have t power of 3, over here is negative 1 power of 3, which gives you negative. So you can form the pattern when you have a Laplace transform for t power of n, then you have negative 1 power of n here, and you differentiate the fx with respect to x in n order. In this example, we are going to find the Laplace transform for negative t sine phi t. So we see this function ft is equal to negative sine phi t, and you multiply it with t. And you know that from this property, if you multiply the function with t power of 1, over here it will be negative 1 power of 1, which is negative. So over here is differentiate with respect to x for your capital Fx. So let's recall the Laplace transform for sine phi t is equal to phi over x squared plus phi squared. Since your ft is negative sine f5t, then your fx is negative here. Then we need to find the negative dfx with respect to x. When you substitute the fx inside here, you found that negative can be cancelled, so you have a d over dx phi over x squared plus phi squared only. Then you continue with the differentiation, and the x squared plus phi squared can be written in this format, inversion, okay, negative 1, and then you continue for the differentiation with x, and then negative 1 here you multiply in front to get negative, so negative 1 here you minus with 1 to get negative 2, and you continue to differentiate the term inside with respect to x. So in this case, x squared will become 2x, and phi squared, after you differentiate, you get 0. So this is the answer. And we can simplify it into this format. You can see that if you have the time domain function f1t equal to negative sine phi t, when you perform the Laplace transform, you get the f1x is equal to this. So when you multiply the first function with t, then we can apply the property here. So when you multiply t in the time domain, is equal to negative d over dx in the Laplace domain. So after you do the calculation, you obtain this result, and this is the Laplace transform result for your t negative sine phi t. Let's continue with the next property, which is the integral of transform property. We know that when we perform the Laplace transform on the ft, you get the fx, where your x bar has a region of convergence within x to infinity. We would like to know, if we integrate the fx with respect to x, what is the change in the time domain signal here. Therefore, we can continue with the proof here. So we want to find the integration for fx here. So we can form the fx equal to this Laplace transform definition. Let's solve the exponential with s term inside this integration, and then we can get this answer, exponential negative xt, where negative t is your constant. After integration, you need to divide it. So when you substitute infinity inside this, you get 0, and substitute the limit x inside it, you get negative xt. With that, this can be cancelled. We will get the ft multiplied with the 1 over t, which is the ft over t, exponential negative xt. So based on the definition for Laplace transform, you can form it to be Laplace transform of the ft over t. This proof shows us that if we integrate the Laplace transform like this one, it means that we are taking the ft and divide it with the t. So the effect is your ft will be divided by t if you integrate your Laplace transform result. We can use this property to solve this example. So let us try to find the Laplace transform for this function. So this is your ft function. And you want to find the fx. What is the answer? We know that when we take the Laplace transform for sin phi t, you get the fx equal to phi over x squared plus phi squared. In this case, you have the sin phi t divided by t, so in your fx, it will be integration with respect to the dx. So to solve this integration, we can apply the trigonometric substitution. Based on the x squared plus phi squared here, we can let the x equal to phi tangent angle. And your ds, in this case, if you differentiate dx, okay, phi remain, differentiate tangent, you get secant square angle with respect to the angle. Then we can substitute the s to be the phi tangent angle, you can substitute inside, and the ds you can substitute by the phi secant square angle. You can see that the limit for the x is changed to the angle here, because here is dx, here is the angle. So for the d angle, the limit should be in angle. Okay, for dx, the limit should be in x. So based on this formula, you can obtain the angle. Your angle will be just take the arctangent and then s over phi. And don't forget the bar. So when your s bar is equal to s, then your angle will be this. When your s bar is equal to infinity, so you substitute infinity inside here, infinity divided by 5, you still get infinity. With that, you obtain this limit. So we can solve the integration component here, where you can see the phi square can be taken out, and then you have the tangent square angle plus 1. So this is secant square angle, which can be cancelled for these two terms. These two terms can be cancelled as well, so you only have 1 inside. With that, if you integrate with respect to 1, then you get the angle. So this is the lower and upper limit. This is the graph for the arctangent, where you can see that when your angle is close to infinity, okay, you will get some number close to pi over 2. So with that, we can substitute this number inside. So this is your final answer. And when we perform the Laplace transform for this ft, you will get the fx equal to this answer.